We left off talking about optical properties, particularly color. Something that we did was we talked about how you can dope things, right? This is glass where we've added a bit of chromium oxide and a little bit of cobalt oxide. You can get very nice colors coming out of them. So you guys have probably all done this in 2010 if you've taken that. We talked about how some materials you get absorbing. It absorbs one color, and therefore, since that color gets absorbed, everything else gets through, and so you see the complement, right? So this is actually absorbing blue, and that's why you're seeing this yellow-orange color, right? We've used this E equals hc over lambda equation to calculate what the band gap should be from the color, right? So I could give you like a red powder, iron oxide, right? Like a hematite sort of red powder, rust color, and I can say what might be the band gap of this material. And you say, well, I'm seeing red. If I gave you a little color wheel, which I would probably have to do, will color wheel work, or does it have to be a complementary color wheel? No, it's like it. So, right, so that means if it's red, that means you're absorbing in the greenish. So if you had this table here, you could say green is around 550 nanometers. So you can turn that into electron volts, right? Everybody clear on how you do a question like that? All right. What was phosphorescence? Somebody remind me what's phosphorescence, and is it useful for anything? Yeah.
Basically, it's just like a material's ability to absorb electrons and like go back down and emit light.
Yeah. Think of it, whenever you hear phosphorescence, think to yourself, this is a short-term temporary process. Something happens, it gets bumped up in energy level, it's gonna relax back down later, but right, it's a temporary process. And as it gets hopped up, and it can undergo actually several different transitions, it doesn't just be like up and straight back down, it can undergo a series of smaller steps. It can involve phonons, right? So actually, they can be complicated. I'm not gonna go into detail in this class, but it can be a series of steps, but as it decays back down, it usually corresponds to a very specific energy change, therefore a specific wavelength. Yeah.
So with these lights, they just have tons of small steps which cause it to emit all wavelengths of light?
Fluorescent lighting is different. It has something...
So what I said in the book is that it coats the outside of the tube with ceramic, and then it excites it, and then it emits like all wavelengths of light.
Yeah, so what you have... Let's actually pull this up. How do fluorescent lights work? Because there's a pretty good diagram. Because there's LEDs and there's fluorescent lights, and they're not the same thing, right? So what we want is right here. Here's your phosphor, right? So your phosphor is actually what's giving off the coating. This is going to be your ceramic material, right? But how these work, it has to do with the mercury gas that's created inside of here. And I don't recall the exact mechanism. This is different than LEDs that look bright white. LEDs are the ones that include the YAG on them. So if we go to LED structure. If you look at an LED, they've usually got, let me see if I can find one. Like right here. You've got, no, that's not what we want. Because LEDs would give off like a whatever color of the wavelength, right? So here they've got like N-type gallium nitride and P-type gallium nitride. So they've got a PN junction. That makes an LED, right? Whenever you got P and N together, that makes an LED. But if that gives off light, it's going to give off light of a specific color corresponding to this gallium nitride band gap. And you probably don't want that unless you want a colored LED. If you want white light from an LED, how do you get it white? You have to add...
Yeah, phosphor on the acid.
I think maybe that one. Let's show it. Oh, where'd it go? No. I'll know when I see it. It is... They add something on top of it, and I'm not finding a good image.
Maybe you say it's not white LED.
Yeah, let me try that. Anyways, they have... Okay, right here. Right, so this is how white LEDs work. When you want to get that, here's your P-type. Let's see, P-type. So this is your LED, right? Your primary light source. This is giving off colored light, though. This is one wavelength, whereas white light is kind of all wavelength. It's actually skewed away from blue, right? And so what it actually does, these blue photons, that's what this is coming from, this primary light source. It actually goes into this sapphire substrate secondary light source. This is your ceramic right here, the secondary light source. This is going to be giving off white light. And they typically use YAG, yttrium aluminum garnet is a really good. Why do they use that? Because it has bonkers high efficiency, like 95% or something, right? Light comes in and you get basically 95% of that light coming out. It's just changed wavelengths, right? So really, really, really efficient. In fact, where's your inefficiencies? Why do we use LEDs for lighting? They're crazy efficient. How does like incandescent lighting work? It's heat, right? So clearly you're heating this thing up to 1,000+ degrees, and now when it gets that hot, it's giving off black body radiation, right? And that's why it looks white, right? Because it's giving off radiation of all sorts of different wavelengths. But because it's heating up like that, it's just terribly inefficient. I don't know what the number is. Do you know offhand, Josh? What's the efficiency of incandescent lighting? I'd put it around 20%, but I have no idea.
5%.
What's that?
Maybe 5%.
It's not going to be good, right? Now here, where's your inefficiencies going to come from? Recombination. Yeah, right? What's that? Well, recombination is kind of what actually you're going for, right? Recombination is what's happening here, right? So if we remind ourselves how an LED works, you've got your Fermi level will be constant, right? You've got P and N type, right? So let's draw our N type here, our P type here. So it's going to have some band bending, right? And what are we doing to make this thing light up? Which way do we want the current to go? We want electrons to go that way, right? Because then electrons will travel up here, and all of a sudden they'll realize, like, why am I here when I can drop down and recombine? So we want recombination. When I can drop back down here to find a hole and recombine, right? So you actually want recombination. That's how you get light coming out of these things.
But in LEDs, the inefficiency is more recombination. It's not every electron will pair.
Okay, so if some were to leak through, that would cut into our efficiency, right? Because it takes energy to drive these things uphill in terms of this, right? So we're actually driving. That's why I have to plug LEDs into the wall, right? Because it happens spontaneously. So you're driving them there, and if some were to leak all the way through, then it did turn into light. That would cut into your efficiency. Where else do we lose efficiency? Yeah.
Do we lose it in the propagation through the other substrates?
Yeah, so if the light doesn't get out, let's say that this light gets absorbed somewhere here and it doesn't actually create the other white light and get out. So if this isn't very transparent and it blocks that light, then we lose that. That loses some efficiency. Anywhere else?
Having impurities
What would they do?
won't allow the electron to drop all the way back down. It might drop somewhere else.
Yeah, you might get, and then that might be too small of a wavelength to actually produce white light. So there are things that can cut into your efficiencies, but by and large, what's the efficiency of an LED light bulb? Let's look it up. I don't know the number offhand. It's really good though. LED light efficiency. They are bonkers good. So let's see. Extraction efficiency, it depends on your refractive index. They put these things on top of them. Anyways, you are easily looking at, very, very, very efficient.
Right? Google said 5% in this.
5%. So if this number is true, if this extraction efficiency is true, we went from 5% to 70%. I'm not sure if those are the exact numbers, but they're going to be something like that. This is why it's so important that we find ways to go from incandescent to LEDs, right? This is why I replaced all of them in my house. Well, rather, as my incandescent die, I'm replacing them because I'm slow that way, right? Because they are expensive, right? I think they are currently receiving a slight subsidy, and every state does it slightly different. There's a slight federal one. So when you buy these things, they take a little bit of the edge off of buying them, but they're still, it depends on what you're buying. My can lights in my house are $7 or $8 a piece, right? So they're not cheap, but they're going to last for 25 years, for one thing, rather than how long does a regular light last? Not very. And it's going to be 70% efficient, right? So my power bill should be going down and down and down the more these are replaced. Yeah, Josh?
The university student apartments where I live, they have like the RA who coordinate the courts. You replace all your light bulbs if they go out and they're all
Yeah, and if you do it one at a time, it's really not very painful. So what I do, I go to Home Depot and I buy 10 of these things, and then as my things start dying, I just replace them all the time. When that's out, buy 10 more. So do what you guys want, but I think that's a good way to do it because you don't have to eat the $500 up front or whatever they do. So why have we not done this up till now? Why did it take us so long to move to LEDs, right?
Cost of manufacture.
They're not cheap, and they're getting cheaper the better we get at it. Do you have an idea too, Eric? the same thing.
I was going to say that they might not have basically like proper pigments.
That was the real problem, right? To get to this, I think we've lost it. Maybe it's here, right? Oh yeah. So this structure here, you wanted blue light to come off because going from blue to the other colors is it's easier and it's more efficient. But we didn't have a good blue LED. In fact, this was a Nobel Prize last year. Shuji Nakamura at UCSB won the Nobel Prize in physics. It must have been physics, because he invented the blue LED. And now that you've got the blue LED, now you've got blue laser pointers, right? You never saw blue laser pointers when they first came out. They're always red, and then green came along. And now if you go to a fancy place, they'll have these blue ones, right? Inventing the blue LED led to the blue laser, led to way more efficient lighting. Now, in fact, you can have a TV that has RGB LEDs, right? So you can get whatever color you want by mixing 3 different types of LEDs, right? So it was a really big technological advancement, and it wasn't that long ago that this happened, which is why now LEDs are becoming more and more of a no-brainer to put in homes. They're even better than fluorescents. I wonder what fluorescent efficiencies are. I know they're good, but LEDs even blow them out of the water, right? That was a big tangent, but good question, whoever asked it. Actually, so one of the problems with these, this is the diagram I was looking for, right? This is your LED right here, right? LEDs, the whole thing looks like it's that big. The tiny little light emitting diode part of it is tiny down here. This is all going to be your phosphor to turn it white. And then you have this lens that makes it, rather than point straight out, kind of makes it diffract diffusely, right? So most of this is not even the LED. Most of the structure, that's your LED, this tiny little thing down here. Most of it is actually packaging and getting the light to direct the right directions and change the light's color, right? Very little is actually generating the light. Okay, so here's our LEDs. I think we've said enough about them maybe. One more thing about phosphorescence, that you can use this time-dependent decay, from it goes to its elevated, excited state down to some other state. You can use that to do things, right? And I give you one example, but there's many, many others. You could have a contact-free thermometer, right? So if your turbine engine is spinning many, many times per second, there's no way you can touch it and measure the temperature. Instead, you can pulse it with a laser, really easy to embed in your system. You can look at the light that gives off. It's going to be a very specific wavelength, so you can make a sensor that just detects that one energy wavelength. You can monitor it, and you can basically say, oh, it's decaying at, whatever that is, 1 per second, right? That's the half-life. Then it must be at such and such a temperature, right? And these exist over a pretty wide range of temperatures, right? So they're a very nice tool in that regard. And you can do other things with them. What would you guys do? What would you do with decay lifetimes? What information, or what devices could you make out of it? Maybe turn to a neighbor and brainstorm for a second. What might you be able to do if you could control the rate at which something decays?
Carbon dating.
What do you guys think?
How they do carbon dating?
Is it fluorescent? It's half-life, but it's not fluorescent half-life. You're right. That's a different type of half-life. How could you do optical half-life? What could possibly be used And I don't have an answer here, so I'm looking to you guys to be creative. I gave you my example. What could you use these for? Anybody got an idea? I guarantee if we were to Google it, we'd find a whole bunch of it would be feeling silly. Barrett, what do you think?
I'm just wondering if this is how those little gun thermometer things work. See, those are you point it up at an air vent and the temperature of the air.
Nope, that's a different mechanism. Those are cool, different mechanism. It doesn't use fluorescence decay. That just uses black body radiation. So all things are emitting radiation. It's measuring that radiation. Anybody thought? Any thoughts on this? This is glow in the dark. That's exactly what this is, right? I'm sure there's other mechanisms whereby this works, but this is at least one mechanism to achieve something that glows in the dark. You pump it full of light, right? You hit it with some intensity. You activate a bunch of these states, right? And then there's some time constant as they're going to decay back down. And as they do so, they're going to give off light, right? So glow in the dark, strips and films, absolutely use this for this. Anything else? Maybe we'll make this a homework question for you guys to find the cathode ray tubes.
Like an old TV.
Did they use fluorescence? Did they?
Yeah, the electron kind of.
Really? And that's how it lit up?
Yep.
Interesting.
So there was no
Huh. I should know that. That's like a relic from a bygone era at this point. Very cool. Other questions or any other thoughts on what you might use these for? Yeah.
You might be able to make some kind of sensor, but there's probably better ways to do that, so.
Yeah, it'd be a nice like physical sensor because you can move it around. And we actually use these when you align X-ray systems. They're really nice, or laser systems for that matter, right? I've actually done it for both. In grad school, we had a laser system. Have you guys ever seen these optical tables with like the lasers bouncing around all over the place? In this process of moving it from mirror to mirror to mirror, it's helpful to take one of these phosphorescent papers and hold it in the laser path, and maybe it's a pulsing or a regular laser, but you can see where the beam is where you wouldn't otherwise be able to see it. So you can move it, say, okay, it's going this way, because you're just holding it and you're seeing it on the paper, because it's lighting the paper up and then it's glowing, right? So you see the glow on the paper, yeah?
In like your stereotypical like radar system in a submarine that like goes around,
Uh-huh.
that's probably what this is.
I wonder what those are now. I have no idea. But plenty of applications for this. Like, let's say, how about this? You want to do XRD on a sample, but you don't want the XRD beam to spill off of your sample. Your sample's maybe like the size of a pen. But you know, as you go to lower and lower angles, the area that it illuminates gets larger and larger, and you don't want it to spill off, right? For a number of different reasons. So this is what I'm describing. Let me just draw it here. Right, you've got X-ray light coming in, right? And if you're at a really low angle like this, then your sample is sitting right here. Your X-ray beam might be spilling off of your sample. What's problematic about that is then when you get to high angles, it's no longer spilling off of your sample, so it gives you a really weird background. Your background is a function of 2 theta angle. It's going to be low down here because it's spilling off, and then it'll go up. Right? You'll see that weird background, which will be hard to fit. It leads to other problems. So how do you avoid that? You could take your little phosphor strip and set it on where your sample normally goes, and you can see how much area gets aligned, right? How much is getting hit by the X-ray, which is causing it to luminesce. And you say, oh, it's about 5 centimeters, and my sample's not close to that big. But at this angle, it looks like it's the right size, right? So these are just they're very handy things. I'm sure we could think of many, many other applications for them. All right, how does the laser work? The neodymium YAG laser, solid-state laser, how does this work? It's pretty clever. They've got this neodymium YAG crystal, this is the laser medium. This is critical that they choose this material because it has an elevated state, and then when it relaxes down from that excited or elevated state to the lower state, it has the wavelength that you're looking for, right? So when you choose to use neodymium YAG crystal, that's fixing your wavelength, right? That's giving you a wavelength that you're not changing at that point. What they do is they make these surfaces really, really smooth so that this thing can enter and exit this. And then they put partially reflective mirrors, or fully reflective mirrors even, right? So this one is completely reflective. This one they're going to call it partially reflective. So maybe 1% or 2% of light gets out. The rest of it goes back in here. As it's going back and forth in here, it's exciting more and more of these things back up. So you're accumulating quite a bit of light bouncing back and forth in here. And you either have a partially reflective mirror, so part of it's leaking out constantly, or they'll have a shutter that opens up temporarily, right? This is how lasers are working. Again, if you dope it with different things, it's the dopant that changes the wavelength, because it's the dopant that's probably the activated state, right? So you can dope it with neodymium or chromium. Lots of different things you can dope these things with. This is a sapphire laser, chromium and alumina, that's a sapphire laser, or ruby laser, ruby, sapphire, same thing. Yeah, Jake?
So does the strength of your laser depend on how partially reflective your mirror is? So if
Yeah.
you shutter, would that be?
Yeah, exactly. If this was less reflective, more of it gets out, then basically you're going to have a higher intensity at constant operation, but a lower intensity at burst, right? So a lot of these lasers actually they're pulsed lasers. If you guys, anybody work with Tuari? Do you work with Tuari? Anybody work with Tuari in our class? So he's got a pulsed laser deposition system. And his delivers actually a really high amount of energy and pulses by containing this for a moment and then releasing it, containing it and then releasing it. So it gets enough that it can melt or ablate materials, right? Whereas if you want like a laser pointer, you don't want high energy, right? You don't want to damage people's eyes or go in their eyes. So, and you want it continuous probably. So then they do like a continuous production, right? And they try and excite fewer of these because you don't need to be melting things with a red laser for a laser pointer, right? All right, let's talk about index of refraction. I think we left off here last time. We said that, okay, a great way of delivering information would be via pulses of light, because light moves so quickly. But the challenge is that light, even though it moves quickly, it can't bend very easily, right? You'd have to like bounce off a mirror. Like I've done that. I've aligned like a laser table in my first year of grad school, and it was horrible. Like it's really hard. Aligning those is not pleasant. And you can never do that to every single home. And then what if somebody were to reach their hand in the way and get hit with the light or block the light and just block transmission, right? All sorts of problems. So we needed a way to transmit light. And so clever people realized that, hey, we can make a type of glass that when you send light into it, it can't escape. Now, how on earth does that happen? It's based off the concept of index refraction. Maybe in physics you did these calculations, right? It essentially says that light changes its velocity as it passes through different materials. So it's got a slightly different velocity, right? It's a little bit odd. We think of speed of light as being constant. It's changing velocity, though, in different materials, right? So if you got your angle of incidence, let's say light's coming in like here, right? Depending on the index of refraction difference between these two materials, in this case air and water, your refracted ray is going to be at a different angle than the incidence angle, right? So this might be like 45 degrees, and this could be 10. This is the exact problem if you ever try to go spearfishing or just touch anything in the water. You go to stab it, and all of a sudden your straight stick looks like it bends in the water and doesn't go where you were looking at, right? Because you're seeing something that's refracted, right? So it's tricky, right? So the same exact thing happens whether it's visible light or non-visible light. You can use UV light and get the same exact effect, right? So if you control the index of refraction between these two materials, you can control what this angle is. How do we use that for total internal reflection? Right, so what I mean is you've got a cable here, right? This is typically glass, right? A fiber optic cable, glass. And you don't want your light to escape, right? You don't want it to ever leave this thing. So how could you take advantage of this principle to make sure it stays inside always? Yeah, Barrett? Yeah, basically the condition that you want to confirm is you want this. You want, if this is your index incident angle right here, what you don't want is anything to get out. So you want this angle right here, if we call this like theta, you want it to be at least 90 degrees so that at worst your light stays inside, right? So that's easy enough to do. All you have to do is find the material that has the right index of refraction and the right appropriate initial starting angle. This one here, as we call it. Call that alpha or something, right? If you're not going to change the index of refraction of the material, say glass is, I think it's like 1.4 or something, you can't change that difference between air and glass. Then it basically says as long as you introduce light at an angle that's this or less, then you're going to get total internal collection of this light. Which they do, so when they pulse these things, they introduce it at a relatively steep angle. It bounces through here, but it can never actually escape. It stays trapped inside of it, right? Now, it actually does escape. Who's taking EPS? What do we call that section that escapes, Chris? Cohen's so disappointed.
I remember what it looks like.
I remember what it does.
It slightly leaves, right? They call it an evanescent wave. Right, so it actually, every time it bounces the edge, it actually does leave slightly for reasons because of physics. I don't recall. Right, but it actually leaves this slightly. What do we use that for? In material science particularly, we've got a really clever machine that takes advantage of that. FTIR. What type? They call it ATR, attenuated total reflection. Attenuated, it's ATR something. But it takes advantage of this. Basically, you have a crystal here. It's usually something horribly toxic. I don't know what they are. They're not nice crystals, but it's one such that your light, the IR light that you're going to probe the material with, it can sort of touch your material just like that. So if your material is some big block up here that is totally opaque to the light, the IR light, meaning you just absorb all of it. If it absorbs all of it, you can't get any information out of it. So instead what you do is you put one of these crystals on it, you have your IR light bounce through here. Each time it hits an edge, it's touching your sample momentarily. It's interacting with it. It's either going to get, right, it's going to see either its peak go up or down depending on how it interacts with the material. If it's absorbed or it gets this boost from the material, right? And then when you're done, it's going to bounce back over here to your detector, right? It never has to go through your material at all. It just touches it a bunch of times along the surface. So we take advantage of this all the time. Clearly, the most important for society, though, is fiber optic cables. Just hugely, hugely important. Yeah, Barrett?
I remember Cohen told us that it was used, like that property was used to spy people, or that they would put like another fiber optic cable really close to the other.
Oh, really? And
so
it would snoop some of the information?
It would steal some of the information.
That's really clever.
And they were trying to counteract that. They would have stations along the fiber optic cable that was seeing what the intensity was. So
And if it was
one drop
dropping.
between 2 stations, you would know exactly where the spies
Oh,
were.
that's really cool. That's really cool. Cohen, I think he was a spy. I'm like 99% sure that Cohen was CIA or something. Okay, so again, this angle, this is your index of refraction. It's going to be related to the difference in velocity between your two media, right? So every two materials are going to have a slightly different index of refraction, and this index of refraction will be related to the angle. I guess I'm calling it R here, so I should R. Switch it. The angle at which you'd have to introduce your light to have total internal reflection, meaning fiber optic. For glass things, it looks like this instance angle is angle of instance 1.5. Sorry, index of refraction is 1.5. Therefore, you have to introduce light at less than 42 degrees. Otherwise, you're going to lose some of it, or lose all of it. Actually. Okay. All right. I think that's all I have to say on this chapter. Yeah, that's all I have on this one. Any questions on anything we've covered? So let's do the rest of today on reviewing, I think. And then on next class, I'll pick up and we'll start with chapter 12, which is the whole latter half of this class. We've done properties like crazy. The whole rest of this class is on how do you make these evil ceramics. And there's a lot of tricks we can teach you, but in general, it's just hard. But we'll teach you what goes into it and what's the science behind why they're so challenging, what's happening and driving that. So what questions do you guys have now? Yeah, Jared?
Can we go over Navarro herring versus cobalt?
Yeah, let's do that. That is a good question. So we go back to time, temperature, and environment because it's creep. So you've got diffusional creep, that's Navarro herring. And then this one I didn't call it cobalt, but in the question I do. But this one is, whenever it talks about grain boundary, that's cobalt creep. Right?
So Navarro herring is diffusional creep.
Meaning through the bulk, through the lattice, if you will. So you have a homework question on this. I asked you to say which is it going to be? Is it going to be lattice Navarro herring, or is it going to be grain boundary creep, cobalt creep? And I give you the diffusion constants for the two different species through both grain boundaries and lattice. You're going to figure out which one's faster. Are both happening? Yeah, you betcha. But one might be happening like 1,000,000 times faster, which essentially says you can ignore the other one. And I'm guessing that's what it is on this. And I haven't worked it out yet. I'm guessing one is much slower than the other. I just haven't done it yet. Right? So what's the driving force for this? I think one of the key things I want you to remember from this class is what drives Navarro herring creep. Right? We said that you had a material which when you pull it or push it, right? Let's say you're pulling it like this, so this is under tension. Poisson's ratio says there's actually this compressive force acting on it, right? Or maybe you set it up such that you've got both tension and compression. Regardless, you've got a region where atoms are being stretched out more than they'd like to be, here and here. And you've got regions where they're being compressed more than they'd like to be. How does it respond to that? Clearly, things are being stretched out more and compressed. This crowded area is going to start to move up there, right? And this empty space that you create by pulling this is going to move that way. So we can talk about that in terms of mass and vacancy flux, right? Flux is movement of number of something for an area at the time, right? So things are actually moving. You're getting mass moving from here, from the crowded region, up to the less crowded region, right? What's the driving force for that? Anytime you have a flux, anytime in material science that you have a flux, you have a driving force and a constant proportionality, right? If it's heat, what's your driving force for heat movement through material? Temperature gradient. And what's the constant proportionality? What tells you how much heat travels per difference in temperature? Thermal conductivity, right? What about mass? If it's mass transport, what's your driving force? It's a gradient in concentration, right? It's dc dx. And what's your constant proportionality? What tells you how much mass moves in response to a gradient concentration? Diffusion coefficient, right? So we could calculate the flux, and I was going to do this on the test, but I think it's too hard, so I quit. Actually, it was there when I was trying to do this myself, and it was not going to work. But we could, if we spent some time on it, we could figure out what's the average size of a grain, right? So what's the cross-sectional area? I call it like a micron squared, right? So after like 2 hours, we have a time and we have a cross-sectional area. We can figure out what's the flux of atoms going across it, right? Right. To do that, all we need to know is we need to know dc dx, and we need to know the diffusion coefficient, right? So how do we get dc dx? We have these nice expressions. We say the concentration at any given point is equal to the initial concentration of vacancies, right, So maybe there's like 1 in a million, right, normally. But we're going to modify that by multiplying it by exponential of the stress that we're applying times the average vacancy volume divided by the thermal energy. This has units of energy. This better have units of energy. Does it? Stress times volume, is that energy? Well, what's the units of stress? Like pascals, right? So we've got Pascal times meters cubed. Is that energy? Yeah, you betcha it is, because a Pascal is a joule per meter cubed, right? So units cancel out. In fact, this is energy over energy like it ought to be, right? So basically, what started out as 1 in a million, maybe this is going to be a positive number. Right? Should this be positive or negative? Exponential of a positive number is going to be a positive number. So this actually got larger. So we have more vacancies under tension. Right? That makes sense, right? That's the portion where I'm pulling it apart, right? So they're stretched out. I'm going to create more vacancies there, right? So we have more than our average amount. Meanwhile, down here, the exact same thing but negative. So it's going to be compressed together. So we have fewer vacancies. So we have dC dx across this grain, right? So if this was like 1 micron across, we could calculate dC dx, right? We could calculate our driving force in terms of vacancies, right? Then all you need to know is the diffusivity of vacancies in this material, right? What's the rate at which the diffusion coefficient at which vacancies travel through the bulk of this thing, right? And that was going to be a tough question, but it will not. That's too hard.
But will we still have the question on Friday?
Oh, you betcha. I'm just not going to do that hard one. Yeah.
So for the problem on the homework, it asks alumina, which one will happen, Koval or Navarro?
Okay.
And since there's a compressive stress of it was like 200 megapascals, would it be Koval creep?
You'd have to calculate it.
Or you calculate
Whenever it asks you to determine whether it's Navarro herring or Koval, go ahead and calculate it for both and see which one's faster. And then remember, if you've got 2 species, how does that change the picture at all? Because you've got, in order to actually grow this grain, can you just move aluminum and leave behind oxygen? No, because aluminum's got a charge for one thing. So the more it goes, it's going to eventually build up an electric field that will stop further aluminum motion, right? So they both have to be able to travel. So you've got 2 different mechanisms, right? Navarro herring, Koval, and for each one of those mechanisms, you've got aluminum and oxygen species, and it's going to be limited by the slower species, right? So if oxygen happens to be really slow, or if aluminum has to be really slow, whichever one is slow, that's what's going to limit that mechanism. So you're going to calculate the rate of each mechanism on its slow species, and then you're going to calculate which of those 2 mechanisms is fastest. Fair enough? Other questions? And this is just 2. There's other mechanisms, right? This is 2 of the most common ones. You'll learn about others later. Not in this class, though. Barrett?
For the Koval creep, would we have to find out what the grain size and for that, or would that be?
Well, yeah, so the expressions for these things, if you go to our first expression, so I didn't actually give you, I said this wrong, I'm sorry. This is still Navarro herring. I didn't give you in the notes an expression for Koval creep, I just did on the homework. So I'm not going to ask you any more details on Koval since we didn't talk about it in class. I will give you the expression for it and have you use the expression. But here's the expression for Navarro herring, right? In this case, it's 13.3 times omega. What's omega again? Volume of the diffusing species. In this case, it's going to be the vacancy volume, right? How on earth would you get that number? How would you come about vacancy volume? Any ideas? But the volume of an individual vacancy, of an oxygen vacancy, what would you do?
Well, in the homework you tell us to
Oh,
look
did I
up
give
the
it away?
volume.
Oh, I gave it away. All right. How do you do it?
You look up the volume, well, you find the volume and you divide it by the unit cell volume by the number of atoms per unit cell.
Yeah, so let's do an example. The perovskite crystal structure, it's cubic, right? So I could give you the lattice parameter, it's 4, right? Or 5 or something, okay? So you know the volume of the unit cell. What would be an approximation for the oxygen vacancy volume? Right, so if you know the perovskite structure, right? I just said that this length is 5 angstroms, right? Then do a quick calculation with your neighbor. What would be the approximate oxygen vacancy volume? So the approach here, you take the volume of the unit cell, you're going to divide it by the number of atoms in the unit cell, right? So we've got 5 times 5 times 5. What's up?
Recently, each atom takes up the approximate amount of volume in this case.
That's what his assumption is. That's not the case, but it's an okay approximation, right? Especially if you're just doing ballpark calculations. What's the approximate rate of strain? It's a pretty good approximation, right? So you're going to do 5 cubed, 5 angstroms cubed. How many atoms are there per unit cell? You got 5? 1, 2, 3, 4, 5. Yeah, you're right, 5. Right? So that would give you an approximate volume per atom. And then we'd assume that an oxygen vacancy is going to be roughly that. In reality, it's going to be a little bit bigger because oxygen ions are a lot bigger than those other things, right? And so there's a whole lot of work determining the actual volume of these things. We're just not going to get into this class. It's a pretty good approximation. Okay? Then you've got D, that's the diffusion coefficient. What's the diffusion coefficient depend on? 2 things. The activation energy, right? And the pre-exponential. So I'd have to give you, to solve for D, you need to know D naught and you need to know Q, right? The activation energy for diffusion. Because you'll remember that D equals D naught exponential of negative Q D over K dt. Right? That sound familiar from somewhere? And then the stress, all divided by, now this is small d, and that small d is the grain size squared kt. Okay? In the homework, you'll remember that these expressions look pretty similar for Navarro, Herring, and Coble. They look pretty similar, but there was a difference. For Coble, which is diffusion along the grain boundaries as opposed to through the lattice, you have to have an extra term up here that we call delta, and that took into account the size of the grain boundary. Is the grain boundary 1 angstrom thick, 2 angstrom, 3 angstrom thick, right? So we give you a value for that in the homework. And then the other difference is to make sure the units work out correct, that actually makes this end up as dq. So that means that you expect very different dependence in terms of strain as a function of grain size. One goes as 1 over d squared, and one is 1 over d cubed, right? Which it makes sense. The more grain boundaries there are, right? The smaller the grains are, the more grain boundaries there are, the more you'd expect Coble to take off, which it does. Okay? Other questions?
So if it doesn't, would you be giving us the grain size?
I'll make sure that you have enough information to solve the question I give you. I only once in my 4 years here gave a test question that wasn't solvable. And Z actually told me, and I was like, no, I can do it. And he's like, no, I don't think you can solve this. Only once has that happened. And of course, he found it. Okay, other questions? No questions? Do we need to review on Wednesday?
Well, come prepared with more questions.
Okay. On Wednesday evening, come prepared for more questions. Yeah, Jared?
I've learned this multiple times, but can you remind me about how you know if something will oxidize on an Ellingham diagram?
Yeah, let's go over it one more time. And if you got a question that like you feel like you ought to know, I don't care. Just ask it anyways. I got no problems with that. Okay, Ellingham diagrams. Ellingham diagrams are pretty slick. Here's the steps. So step 1, pick a temperature. The problem might tell you the temperature. It says, hey, you got a furnace at 1000 C, right? Temperature is picked. Pick a partial pressure of either O2, CO-CO2 ratio, or H2H2O ratio, right? And I'll give you information to maybe solve one of these, like I did on the first question of the homework this week, right? So you've got one of these 3 things, right? Then third step is draw a straight line from the corresponding partial pressure axis. That's the one that goes around this outside, right? Draw a line from there where? To the appropriate C, H, or O, right? Because we have oxygen, carbons, or hydrogens, right? On the left-hand side of the free energy scale. Scroll down just a little bit. So if you were doing hydrogen, well, they don't have hydrogen on this one. They've only got carbon dioxide, monoxide, and oxygen. So the oxygen scale is this inside scale. I recognize you can't read these numbers, that's all right though. You would draw a line from, if this is where your partial pressure of oxygen's at, you draw a line from here up to the oxygen. If you're doing the carbon scale, let's say you're like here in the carbon monoxide or carbon dioxide, you draw this to the carbon, right? And this one they've drawn it right. These little lines that start sticking out, they should be pointing towards their appropriate this or that. It should make it easy to connect the lines. So that's step 3, I think it was, right? Step 4, see where the temperature and the line intersect, and this is your point on the Ellingham diagram. If the line for whatever reaction you want, right, lies above that point, then oxidation is favorable. Energy goes down to get to the line, so the oxide is stable. If the point is below that point, oxidation is not favorable, meaning the oxides are not stable. See that, right? If the point is below that point. If the point is below, let me just, I might need to rewrite this, sorry. Let me redo this. I think I messed up there. Let's just do an example. Let's say that we have a temperature at 1000 C, and I'm going to give you a partial pressure of oxygen. I'll draw it on here, which is maybe like that. And then 1000 C puts it right. Oh, it's got a straight line already. So it's right there. That's our point on this plot, right? So from that point on this plot, I recognize you can't read any. Let me tell you which one of them are. So right here, this is silicon adding, where'd it go? O2 to form SiO2. That's this line right here, right? Meanwhile, up here you've got, that's lead picking up oxygen to form PbO2. Sorry, right? So which one of those reactions is favorable, and how do you know? This reaction, as it's written, is this line, right? So to make this reaction happen, we can go down in free energy. It's favorable. This reaction, the lead picking up oxygen to form lead oxide, is right there at that line. For us to get to that reaction, we have to go up in free energy. So it's not going to happen. Yeah, Josh?
Wouldn't really like to think about that, especially with oxygen. Is the lead oxide, it's not favorable, it'd rather give oxygen to the atmosphere. But where silicon's below it, it's like, no, I don't want to give this oxygen up.
Oh, I see what you're saying, right? So this thing would rather, since going up would take, going up goes up in free energy, and so it would have to absorb oxygen. If you write it the other way, then it would be giving oxygen off, and it would be going down. Is that what you're saying?
Yeah, just because we're at such a low partial pressure of oxygen,
Yeah.
and it's not going to oxidize, no into lead.
And if you're ever confused which one is which, you can look at these and you'll find that things down here are things like magnesium picking up oxygen to form magnesium oxide, as in like violently exothermic, like this will always happen. Potassium, some things like silicon actually is pretty darn low. Aluminum will always oxidize to form aluminum oxide, but then it's only on the surface, right? Things like that you know should be down here are going to be down here that oxidize very easily, whereas things up here like gold, platinum, silver, we know that those don't form oxides very easily. So actually, how would you force it to form? If you wanted, if this is the line for gold, for example, I don't know if it is, I can't read it. How would you make that form an oxide? Okay, putting a bunch of oxygen does what to this diagram?
It makes your
This is partial pressure of oxygen. Make it 1, and you're based up here. Okay, so you're talking about a line that goes right along here, and then what temperature you got to go to? Yeah, you'd have to be below, this is like 1500 C, you'd have to be below 1500 C, right? And it would oxidize, pure oxygen, okay? For whatever that metal is, okay? All right, coming with more questions on Wednesday. Wednesday in class, we'll start chapter 12, which will not be on the exam, and then at 5 o'clock on Wednesday, we'll do the exam test review.